Today let's move on to nuclear angular momentum or nuclear spin denoted by I. Angular momentum of nucleus is combined contribution of orbital motion and spin motion of nucleons inside the nucleus, and it is analogous to the motion of Earth around Sun. Coming to angular momentum, nucleus has properties analogous to that of electron. Similar to atomic electron, nucleons also undergo orbital and spin motion designated by orbital angular momentum L and spin angular momentum S. The coupling of individual L and S of individual nucleon give total angular momentum. That is, each nucleon has its own angular orbital motion and spin motion, and sum of this orbital motion and spin motion gives a total angular momentum of individual nucleon, and sum of these give a total angular momentum of the nucleus. The total angular momentum of the nucleus containing A nucleons is the vector sum of J. J is the total angular momentum of individual nucleon. J of all nucleons, which is generally termed as nuclear spin denoted by I. So here from this description, I hope it is clear that nuclear spin is the total angular momentum of the nucleus. In the presence of ordinary magnetic field, I splits up into two I plus 1 states, and these substates are equally spaced if the applied force is very strong. The coupling between nucleons are broken, and each individual J splits up into 2J plus 1 substates. At the ordinary magnetic field, I splits up into 2J plus 1 substates, whereas when the magnetic field applied is very strong, thus J of, that is angular momentum of each individual nucleon splits up into 2J plus 1 substates, and it gives out a very complex spectrum. In order to split up angular momentum of individual nucleons, it requires incredibly high magnetic field. So, in normal case, nuclear spin is considered to be the contribution from nucleus as a single entity. So, to be clear from the next session. Nuclear spin is fundamentally related to the sensitivity of nucleus towards effects of external magnetic field. Further, nuclear spin of a nucleus can be determined based on its proton-neutron combination. Look at the even combination of protons and neutrons. Let us consider helium-4 as the example. It contains 2 protons and 2 neutrons. Obviously, from Pauli's exclusion principle, 2 protons of opposite spin pair up, and hence no unpaired proton remains. Likewise, 2 neutrons of opposite spin also pair up, resulting in a 0 spin. So, there is no unpaired nucleon left here. So, this total spin cancel out, and nuclear spin of such a nucleus comes to be 0. That is, I is equal to 0. In even odd case, for example, helium-3, it has 2 protons that pair up, while there is only 1 neutron which remains unpaired. Here, nuclear spin is same as that of unpaired neutron, that is half. All of us know thus nucleons are fermions having spin value, magnitude of spin value is half. then the unpaired neutron contributes towards the nuclear spin of the nucleus, that is I is equal to half. Now coming to odd combination of nucleus, there will be odd number of protons and a odd number of neutrons. Taking hydrogen deuterium H21 as example, it has one proton and one neutron. Both are unpaired. Thus, I becomes 1 by 2 plus 1 by 2 is equal to 1. What I now explained is written as text without having examples. So, we will just go through it. In the case of an odd A nucleus, the single odd valence nucleon determines the nuclear spin I of the nucleus. That is, nuclear spin I is equal to total angular momentum J of the unpaired nucleon. Since protons and neutrons are fermions with a half integral spin value for odd A nucleus, I is equal to half integral value. In odd Z and odd N nucleus, all protons pair up, leaving one proton unpaired, and neutrons pair up to have one neutron unpaired. Nuclear spin is resultant of J values of unpaired proton and neutron, that is I is equal, that is nuclear spin I is equal to total angular momentum of a proton plus that of neutron Jp plus Jn. Sometimes in odd nucleus, angular momentum of core nucleus contribute towards I as I is equal to J unpaired nucleon plus J core. That is, all paired nucleons gather together to form the core of the nucleus, and they form a separate entity, and they contribute towards nuclear spin as a J core, and the total spin will be J core plus J of a unpaired nucleon. And also we can have a very simple explanation of this figure. It will be helpful to understand the direction of angular momentum. That is, this is a representation of a nucleon with the spin in anti-clockwise direction. Just see that. As per the right hand screw rule, the direction of screw movement is upwards when we rotate or when we move the screw. That is, when it is rotated anti-clockwise, the direction of the tip of the screw moves upwards. Just try it. Just imagine it and just try it. And in that case, the direction of movement of the screw represents the direction of angular momentum of the nucleon. Similarly, in the case of a clockwise spin, the direction of angular momentum is downwards. So, if we consider these two as a pair of protons, these two protons are having angular momentum in opposite directions, and that is +1 and -1. These two cancel each, that is spin of these two. If this pair cancel each other, contributing I as a 0. And for even nuclei, nuclear spin is observed to be of integral value. Nuclear angular momentum thus helps us understand the nuclear structure. As we explained, in the case of even Z, even N, that is even number of proton and even number of neutron nuclides, all nucleons pair up to give a total of I equal to 0. That is, all have spin 0 grounds. Then when it comes to b of 0, it is in a ground state. So this is the clear evidence of the pairing effect in the semi-empirical mass formula. Similar to orbital angular momentum, nuclear spin I also has relevant z component Iz, and it is given as Iz is equal to m h cut. H cut is the unit. M is the magnetic quantum number with values minus I2 plus I through 0. So if we consider this variation, it will be 2I plus 1 orientations. So here, let us consider a nucleus with the I is equal to 5 by 2. So, thus in an external magnetic field in the direction Z, this is the direction of magnetic field applied. And this particular nucleus with I is equal to 5 by 2 can orient 2 into 5 by 2 plus 1 is equal to 6 directions. That is from minus 5 by 2 to plus 5 by 2 through 0. And here let us consider the orientation for which m is equal to 0. So this length of the vector shows the magnitude of angular momentum, that is 5 by 2. And coming to next orientation, so let us consider this orientation. From the tip of the vector, we can take a projection towards the direction of magnetic field, that is z-axis. Then it meets at a point on the z-axis, and the distance between this point and the origin gives the value of Iz, that is half, and the unit is h cut. So here for this particular orientation, Iz is a half h cut. And similarly, you can find out how we can arrive at Iz value 3 by 2 h cut, 5 by 2 h cut, and starting from minus 1 by 2 h cut, minus 3 by 2 h cut, and minus 5 by 2 h cut. Hope you followed the class. Thank you.